Hi students, in this lecture I am going to discuss previous IIT problems based on Gauss law. See first one, see the question. Two isolated metallic solid spheres of radii R and 2R are charged such that both of these have same charge density sigma. The spheres are located far away from each other and connected by a thin conducting wire. Find the new charge density on the bigger sphere. So this is a question asked in 1996 for 3 marks. So condition given that solid spheres radius r and 2r same charge density sigma. Separation is very large, connecting by thin conducting wire. So we have to calculate new charge density on the bigger sphere. See how we solve this one. So given two spheres, their radii r and 2r, and for both of them given surface charge density is sigma same, right? Now connecting these two by a thin conducting wire, right? See here what happens when we are connecting by a thin conducting wire. Charge flows from one body to other body until their potentials are the same. Okay. And we are knowing that positive charge flows from high potential to low potential, right? Now, and one more point here, separation is given very large. Okay. That means while taking potential, influence of this sphere on this one will be zero. In the same way, reverse also. So charge on first one, let us take it as Q1 sigma into 4 pi r square. Charge on second one, sigma into 4 pi square of 2r, right? Let us say finally charges are finally Q1 dash and Q2 dash finally. Okay. So condition 1, from conservation of charge, we can write Q1 plus Q2 should be equal to Q1 dash plus Q2 dash. Okay. So we have here two unknowns, Q1 dash and Q2 dash. So we require one more equation. And just now we have discussed that charge flows until potentials are the same, right? So equate now potentials. The potentials equating, it is V1 equal to V2. That means K Q1 dash by R should be equal to K Q2 dash by 2R. Okay. So potential on the surface of a conductor is KQ by R, right? Now you can see this is equation 1 and this is equation 2, right? So here K gets cancelled and R gets cancelled. Then see what we are going to get. Relation between Q1 dash and Q2 dash. Q2 dash is equal to 2q1 dash, right? q2 dash is equal to 2q1 dash. Substitute that in equation 1. See what we have to calculate here. We want to calculate now surface charge density on bigger one, right? Let us calculate q2 dash. So in the place of q1 dash, what I can write in the place of q1 dash, q2 dash by 2 plus q2 dash is equal to. So in equation 1, I am writing in the place of q1 dash, q2 dash by 2. Okay. And this total charge, see how much? This is a 4. 4, 4, 16. 16 plus 4, 20. This is now 20 pi r square into sigma, right? Now from this, we are going to get the value of q2 dash, right? See how much it is. So 1 plus 1 by 2, 3 by 2, 3 by 2. So 2 into 20, 40. 40 pi r square into sigma by 3, right? And we want now surface charge density for bigger one, okay? Sigma value, okay, for bigger one. So take it as sigma 2, okay, for bigger one, I'm taking sigma 2. Sigma 2 equal to q2 dash upon its area. Its area how much? 4 pi into square of 2 or means 16. It is now 16 pi r square. That is equal to, see how much we get? Pi r square gets cancelled. Remaining is now 40 sigma upon 16, right? Then see how much we get? 4 table 10 times, and here, wait, what is this? 40 by 3, right? 3 is there. 3 also is there. Right. 4 table. I think you can take 5, right? 5 table is that 5. 8 times. Sorry, 8 table, right? 8 table is a 5 times. 5 sigma, 8 table. And it is now 2 times 2, 3, 6. It is now 5 sigma by 6. That is now surface charge density of the bigger one after having same potentials. Okay. In the same way, we can calculate for smaller one also. That is q1 dash upon 4 pi r square. Okay. See next problem. A long hollow conducting cylinder is kept coaxially inside another long hollow conducting cylinder of larger radius. Both the cylinders are initially electrically neutral. Right now, see options. This is asked in 2007 for 3 marks. A potential difference appears between the two cylinders when a charge density is given to the inner cylinder. Next one. So regarding his asking potential difference between those two, right? Okay, let us see how to decide this. In fact, we can say directly option. Just see once. If you remember, earlier we have discussed two spheres which are concentric, radius r1, outer one r2. Then potential difference between these two. Let us take it as V, potential difference between those two, that is equal to, if a charge on inner one is Q, then KQ into 1 by R1 minus 1 by R. So this is a previous article question we have discussed in previous lectures. So here we have drawn one conclusion that potential difference it is only because of the charge on inner one. See why it is like this. When charge is given to inner one, electric field will be there. I will take different color to make it clear. When charge is given to inner one, electric field will be like this if charge is a positive. So when electric field is there will be potential difference between those two. Okay. Even this relation also not required to conclude this one. When there is a charge on inner one, there will be electric field. So when there is electric field, there will be potential difference. Okay. Suppose charge is only on outer one. If a charge is only on outer one, field will be only radially outwards. I will show you here. Let us take separately one more diagram for this one. Suppose no charge is given to inner one, charge is given to only outer one. Charge given to only outer one. Then field will be only outside. There is no field inside. Okay. So when there is no field inside, there is no potential difference. Okay. Now exactly same logic coming to here. Only change is now shape. Now shape is cylindrical. Okay. And keeping now one more inside. Right. So now we can say directly from this conclusion, when there is a charge on the inner one, if there is charge, then there will be electric field from inner to outside like this. Because of that field, there will be potential difference. So exactly same logic, only change is now shape. If a charge is there on inner one, there will be electric field. When electric field is there will be potential difference. So directly we can conclude the answer, right? Now see options. Coming to first one, potential difference appears between the two cylinders when a charge density is given to inner one. So this is correct one. And remaining three options, B is not correct, given to outer one. C, no potential difference when uniform line charge is kept along axis of cylinders. This is also wrong. He's saying no. Okay. And next one, this is also wrong. You don't need to worry about charge on the outer one. Okay. We have to focus only charge on inner one. We have potential difference. So only option is A. See next one. A uniformly charged thin spherical shell of radius r carries a uniform surface charge density of sigma per unit area. It is made of two hemispherical shells held together by pressing them with a force F. So F is proportional to. So this is asked in 2010. Let us see how to start this one. Right. If you remember, in earlier lectures, we have discussed electrostatic pressure that is equal to sigma square by 2 epsilon naught. Okay. Electrostatic pressure. Now you can see this sphere is made up of two hemispheres. If you cut like this, you can see this area is now it is a circle, right? Circular part. So force by one hemisphere on other one is taken as that is equal to electrostatic pressure sigma square by 2 epsilon naught into this projection area that is now pi r square. Okay, this is now force acting by this one on this one, or you can say by this one on this one. Okay, so if you want to keep these two together, we have to apply same magnitude, direction must be opposite. Okay, that means answer is now sigma square by 2 epsilon naught into pi r square. Now he's asking proportional to what? So F proportional to sigma constant. I think sigma also given it there. So in that case, we can write proportional to sigma square and r square, right? These two. So proportional to sigma square into r square. Because sigma also variable, r also variable, right? See options. So it is option. We got sigma square by 2 epsilon naught into pi r square, right? So in that case, answer is now first one. Okay, it is very simple one. See next one. The nuclear charge Z is non-uniformly distributed within a nucleus of radius r. The charge density rho of r, this is given charge per unit volume, is dependent only on the radial distance r from the center of the nucleus as shown in figure. We can see diagram here. The electric field is only along the radial direction. That is given that electric field is only along the radial direction. So from this, what we get conclusion is that we should take spherical surface as a Gaussian surface. Okay, right. So total charge ZU distribution is non-uniform. Depends only on the radial distance. Right. Now see questions basing on this. The electric field at R equal to R, independent of A, directly proportional to A square inversely proportional to A. Students, if you observe carefully, question is electric field at R equal to R, right? That means it is now we are taking Gaussian surface, it is just outside the nucleus, right? I'll explain here. It is asking at R equal to R. Okay. That means you can say just outside the nucleus. If this is a nucleus where charge is now Z, if you take now Gaussian surface just outside, now field is E into 4 pi r square. This is now integration of E bar dot ds bar, that is equal to charge inside upon epsilon naught. And this is nothing but Z, right? Nothing but Z. So Z upon epsilon naught. Therefore, E value how much? It is equal to 1 by 4 pi r square, right, into Z by epsilon. So since we are taking at R equal to R, so here R equal to how much? Capital R, right? So this is not depending on A, right? See once. So this is not depending on A, okay? So it is a very simple one, direct one, right? See next one. For A equal to 0, the value of D For A equal to 0, maximum value of D. See what it means. See diagram. A equal to 0 means from the center of the nucleus, rho value decreasing linearly. I am repeating. A value 0 means density decreasing linearly from center of the nucleus. So in this graph, what is given? From center of the nucleus up to some distance, density is a constant. And after that, density decreasing linearly up to surface. Is the point clear? I am repeating. Here, from this graph, from center of the nucleus to up to some distance, density uniform, and after that, density decreasing linearly up to surface of the nucleus. But now question is A value 0. Its meaning is from center, rho value decreasing linearly up to surface. Okay. Now see how we make a diagram for this. And here we have to calculate now the value of D. Right? Value of D. D is the maximum density. Right? Right. See how to start this. So now graph will be according to the given condition. Graph will be like this. Okay. This is given D rho and this is R. Okay. That means rho value as a function of R. See how to write? Positive y-intercept, negative slope. So rho value, negative slope. So minus D by R into R positive y-intercept plus D. Right? Now if you integrate, means if you want to calculate now charge ZD total value, that is equal to integral. This sphere can be taken as a combination of spherical shells. Okay. That means charge is equal to 4 pi r square into dr into rho. Rho value. Rho value, it is 1 minus r by r into d. Okay. So here you have to understand that we have taken like this. This is now nucleus. Inside nucleus, we have taken one spherical shell. One spherical shell. Radius is r. Its thickness equal to dr. Its thickness equal to dr. This thickness, okay, that is now dr. So now what we are calculating is we are calculating now charge in this volume. I am marking here charge in this volume. Okay, that volume is now 4 pi r square into dr into rho. Like this, we have take all spherical shells from 0 to up to capital R. So take 0 to up to capital R. Okay. First take constants outside. 4 pi d take outside. Remaining r square dr. R square dr means becomes r cube by 3. So r cube by 3 minus r square r cube, r power 4, r power 4, r power 4 by 4, and already one r is here, right? Into d, that is equal to ZD. Okay. Now see the calculation part. One r gets cancelled here. We want d, right? Sorry, I have taken d 1 second here. Okay, right. Now from this d value, See how much we get. 4 minus 3, 1. 3 into 4 and 1, 4 gets cancelled. It is 3 3 upon 4 pi 4 pi r cube. Cross check once. 4 minus 3, 1. Remain 3, 4. 1, 4 cancels. 3 comes here. 3 z r cube is left. So 4 pi r cube. This is now d value. Okay. So 3 z by 3 z by 4 pi r cube, right? Okay. Wait. Actually, it is not 4 pi. What we got? 3 and 4. 4 cancel it. Sorry, it is answer is only 3 z by it is pi r cube. There is no 4. Okay. Getting it? There is no 4 there. Only it is a pi r cube. Right. See next one. Electric field within the nucleus is generally observed to be linearly dependent on R. This implies electric field within the nucleus is generally observed to be linearly dependent on R. That means E proportional to R. Students, if you remember, we have solved a question like non-conducting sphere, distribution of charge uniform, then we got E value rho by 3 epsilon naught into R, or you can say R bar. Or we got like same thing in terms of charge, K cube by R cube into R bar, right? So this is when density is constant. Okay, density is constant. So density constant means, see what we can say. So from the graph, density constant means A value must be equal to R. Okay, if A is R, its meaning is up to surface density constant. So here up to where it is A, D constant means density constant up to A. That means now A must be equal to R. That means from center of the nucleus to up to surface of nucleus, density must be constant. In that case, only field is linearly dependent on R. Therefore, A must be equal to R. Okay. Right. See next one. A non-conducting solid sphere of radius R is uniformly charged. The magnitude of electric field due to the sphere at a distance R from its center. So just now we have discussed, right? Non-conducting solid sphere increases as R increases for less than capital R, means inside proportional to R, outside inversely proportional to R square, right? So and graph is continuous. It is not discontinuous. Graph is continuous. Okay. So option is now it is A, right? And see next one. 3 large conducting plates are placed parallel to each other. The leftmost one given charge Q, middle one 2Q, the rightmost one is given 3Q. Separation between the left and middle plates is D, and that between the middle and right plates is 2D. If left and right plates are connected by conducting thin wire, then find distribution of charge on all faces. Okay. See how we are solving this one. So first write down, or first make a diagram for given data. Diagram for given data. Given charges Q, 2Q and 3Q. Okay. Separation given D. This is now 2D. Okay. Right. So we have learned that to know distribution of charge, first what we have to focus is sum of the charges. 3 plus 2 plus 1, 6. That means on outer faces, half of the total is on outer faces, right? See once Q plus 2Q plus 3Q, totally 6Q. Half of that 3Q. 3Q, 3Q. Okay. Now here charge will be minus 2Q because total is a constant, right? So minus 2Q. This is 2Q, 0, 0. But now question is, if we join that left and right one, right? Now see carefully what happens. If we are joining, if we are joining left and right one, okay. So this distribution is before joining, okay. Now after joining, see what happens. Let us make a diagram once again. After joining, after joining, this is a Q, 2Q, 3Q. Okay. Better can avoid this one to avoid confusion. Now after joining, for left and right one, potentials must be the same. Okay. Joining. And the logic what we have discussed to find a charge on outer plates means outer faces. This remains the same 3Q, 3Q. No change in this outer faces. Coming to inside, let us consider this is a Q1 and this is a Q. Okay. Then this will be minus Q1 and this will be minus Q. Okay. Now what I am saying is potential difference between these two should be equal to potential difference between these two. Okay. Let us name them as A, B, and C. So what we can write here? VBA should be equal to VBC, potential difference. Because A and C having same potential, right? That's why between BC and AB, potential differences must be same. And potential difference is given as field into, let us say here field is E1, here field is E2. I can write it as E1 into D should be equal to E2 into 2D. E1 value sigma by epsilon naught, sigma by epsilon naught, sigma by epsilon naught into D is equal to, in the place of E2, again sigma by epsilon naught into 2D. Now from here, D gets cancelled and these two gets cancelled. We get relation Q1 is equal to 2Q2. One condition. Second condition, since it is now isolated, okay, which is middle one, total charge must be constant. That means Q1 plus Q2 should be equal to 2 cube. Okay. So we got two unknowns and two equations, right? So in the place of Q1, I am writing here 2Q2, 2Q2, Q2, 3Q2 equal to 2Q. Okay. That means Q2 value 2Q by 3. That means the Q1 value, how much? Q1, 2 minus 2Q by 3. 3, 2 is 6, 6 minus 2, 4. 4Q by 3, right? Okay. Like this, we can find charges, right?